Good afternoon, everyone, and welcome to our 21st edition of our INFOGEST Viva webinar. My name is Hernandez Olivas, and I would like to introduce Cynthia Fontes, who will conduct this webinar with me. This event is organized by a team of postdoc from Teagasc Food Research Centre in Ireland. This webinar aims to share the latest findings in digestion with presentation from the most recently graduated PhDs, postdocs, and young researchers. This webinar is being broadcast live on YouTube and will be accessible on the INFOGEST YouTube channel. The presentation, this time in a pre-recorded video, will be followed by a Q&A session with the speaker. So I actively invite you to use the Q&A button at the bottom of your screen. Our speaker today is Conor Fitzpatrick with the impact of protein polymorphs, bovine feeding strategy and consumption temperature on the in vitro digestion behavior of selected dairy products. Conor is a PhD researcher at the Teagasc Food Research Centre, VistaMilk SFI Research Centre, and the School of Food and Nutritional Sciences in the University College Cork in Ireland. His research focuses on using in vitro digestion techniques to understand the intrinsic and extrinsic factors influencing the digestion of dairy products. During his research, he conducted a research stay at STLO in Rennes, France, and now he is currently working as program manager in VistaMilk SFI Research Center. So thanks, Conor, for being here, and the floor is yours.
Okay, so hello everybody. My name is Conor Fitzpatrick. I'm a PhD student here in Moorepark, Teagasc Moorepark, UCC and VistaMilk. And today I'm going to be giving you an overview of some of the work that I did during my PhD, focusing on the intrinsic and extrinsic factors affecting the in vitro digestion of dairy products. So I'm just going to start off with a brief thesis overview, just to introduce you to what I did. So at the start of my thesis, I did what I refer to as my knowledge core, where I produced a literature review in the area of dairy product digestion. I then went to look at the intrinsic factors affecting the digestion of milk protein, starting with a chapter that I like to call Small Change, Big Difference, the impact of bovine genetics on yogurt digestion. I also looked at how bovine feeding strategy, so low versus high pasture allowance, can affect the lipid profile of milk, and how that could have a subsequent effect on the release of fatty acids during digestion. I then looked at some extrinsic factors, such as the effect of consumption temperature on the digestion of milk. And I also looked at the influence of both pH and temperature on the activity of human and porcine pepsin. So, just as an overview of my chapter 1, my literature review, part 1 focused on protein digestion. So several factors can influence the protein digestion of milk, such as genetic variation, milk processing, so pasteurization and homogenization, the dairy matrix, so if it's a cheese or yogurt or liquid milk, and then the casein to whey protein ratio. As well as that, I looked at factors affecting the lipid digestion of milk. So I looked at how the co-ingestion of food might impact the digestion of milk, the consumption temperature, again processing in relation to lipids, and bovine feeding strategy. And part 1 of this was published in the Foods Journal, MDPI. So moving on to my first experimental chapter, I looked at the small change, big difference, the impact of bovine genetics on yogurt digestion. So just as an overview, beta-lactoglobulin is a whey protein in milk. Beta-lactoglobulin B versus A differs by 2 amino acid substitutions at position 64 and 118, where at 64, beta-lactoglobulin B has aspartic acid, while A has glycine, and at 118, there's valine for beta-lactoglobulin B and alanine for beta-lactoglobulin A. At position 64, the aspartic acid to glycine reduces the negative charge in beta-lactoglobulin B, which may boost hydrophobic bonding and disulfide cross-linking with casein. This may lead to a potential for higher gel strength in beta-lactoglobulin B. As well as this, I wanted to highlight this as a due diligence study. So in Ireland, there's a move towards precision dairying with a focus on genetic selection of the herd for improved milk production characteristics. However, when we change something like this, we have to make sure that the changes that we implement don't have a negative effect on other areas. So we went and we collected milk from we went and analyzed the herd in Moorepark, and we found cows that produce only beta-lactoglobulin A variant, and we found other cows that produce only the beta-lactoglobulin B variant. So we collected milk from both of these sets of cows. From this milk, we made skim milk powder, and so then we had AA milk powder, BB milk powder, and then we combined these in a 1-to-1 ratio to also make a third powder, AB yogurt, which contains both A and B beta-lactoglobulin. So from all these powders, we produced 3 different yogurts: AA yogurt, AB yogurt, and BB yogurt. We then did some rheology characteristics on these yogurts, and we also did some in vitro gastric digestion. So prior to digestion, we observed visual differences in the yogurts. So beta-lactoglobulin A produced a different yogurt properties than beta-lactoglobulin B, where beta-lactoglobulin B had a firm gel and A had a weaker gel. Beta-lactoglobulin A was associated with higher syneresis than B, and beta-lactoglobulin B was associated with a higher water holding capacity. We then did some rheology, such as viscosity, and we found that what we saw in our visual observations held true, where beta-lactoglobulin B was associated with a higher viscosity than A, and AB was in between, which we expected. Then digested yogurt. So by the end of gastric digestion, we could still visually observe a difference between the yogurts. It appeared that beta-lactoglobulin A had lost its white color, whereas beta-lactoglobulin B really retained that white color, indicating that casein had not been our caseins had been held in the vessel. So when we looked at the release of free amines into the supernatant, we found that at the end of gastric digestion, so after 22 minutes of gastric digestion, we found that beta-lactoglobulin A was associated with a higher release of free amines into the supernatant compared to beta-lactoglobulin B. However, it was interesting that our AB yogurt was related to the highest release of free amines compared to the other two, which is something that we did not expect. So then I want to move on to just a conclusion slide. So beta-lactoglobulin A and B differ by 2 amino acids. Beta-lactoglobulin A was associated with a weak gel, while B was associated with a firmer gel, and that led to A being broken down more rapidly in the gastric phase compared to B. So then moving on to the next chapter, we looked at how feeding strategy can affect the digestion of bovine milk. So we're looking at the low versus high pasture allowance. So this is particularly of interest to the Irish dairy industry, because in Ireland, we're quite unique in the world, where Ireland and other places such as New Zealand are unique in that most of our cows are fed on a pasture-based diet, meaning that they spend most of their time outdoors grazing grass. This is in contrast to most areas of the world where the typical bovine feeding strategy is an indoor fed strategy, where cows are fed a diet of total mixed rations containing concentrates, maize silage, and grass silage. And this leads to a significant difference in the composition of the milk. Now, this is well known, and we replicated it in our study. We found that milk from cows fed a pasture-based diet had higher long-chain fatty acids and monounsaturated fatty acids, whereas indoor-fed cows produced higher levels of saturated fatty acids and medium-chain fatty acids. So then we put it through digestion, and while we studied we studied many different fatty acids, I just want to present 2 here. So when we look at C16, we can see that at the first stage of gastric digestion, despite being higher in the raw milk, C16 is released in greater proportions from grass versus TMR at the first stage of gastric digestion. However, in all other points after this, it's released in higher amounts from the TMR milk compared to the grass milk. Then another fatty acid of importance is conjugated linoleic acid. And this fatty acid is released in significantly higher proportions from raw milk compared to in grass compared to TMR. And then as digestion progressed, we also found that this fatty acid was released in higher proportions at all stages. So as well as that, we can calculate the several health-rated indices from these fatty acids. So in undigested milk, we found that grass-fed milk had a significantly higher unsaturation index, which is linked to health benefits in humans. Following in vitro digestion, we also found that the unsaturation index was higher at all stages of digestion. When we look at the arthrogenicity index, the TMR milk had a higher arthrogenicity index at the final stage of gastric digestion, and the thrombogenicity index, interestingly, had a higher value for the grass-fed milk compared to the TMR milk. We also looked at protein digestion in grass-fed versus indoor-fed milk, and we found no differences, which is what we expected. But is milk protein digested affected by other factors such as intrinsic factors? So we wanted to look at the effect of consumption temperature on the digestion of milk proteins. So we took cold milk and hot milk. So cold milk would be consumed at 4 degrees Celsius, while hot milk would be consumed at 60 degrees Celsius. But by the time this reaches your stomach, cold milk will have increased to 22 degrees Celsius, and hot milk will have decreased to 44 degrees Celsius. And these findings are based on previously published studies that were carried out in vivo in humans. But does this lead to differences in milk digestion? So we were lucky enough to get the Ulysses travel grant to go to France to study in vitro digestion under magnetic resonance imaging, which led to a publication in Food Hydrocolloids. The study carried out started with dissolving whole milk powder and rehydrating it. So this powder came from our grass-fed cows. We then heated or cooled the milk to the desired temperature, 4 degrees, 37 degrees, or 60 degrees. And we carried out a modified in vitro digestion under MRI. Now, when we look at a gastric digestion vessel in vitro, this is the kind of thing we can see. We can start to see when the milk starts to coagulate, and we can see the liquid areas, but we can't really quantify this data. However, using MRI, we can produce images like this. Then, using software, we can clearly see what areas are coagulated and what areas remain solid, or what areas remain liquid. And we can also see things like the movement of lipids during the digestion. So, is there a difference in protein coagulation? So, these are the kind of images that we produced. In the bright areas are the liquid digestion, and the darker areas are the coagulated areas. So, in cold milk, after 2.5 minutes of digestion, there was no difference between the hot and cold milk. However, after 7.5 minutes, it was clear that the cold milk remained liquid while the hot milk had coagulated. After this time point, there was no difference in milk protein coagulation. So this was our expected result. But a not so expected result was the movement of fats during the digestion. So in cold milk, at the middle of digestion, lipids were spread between the top and the bottom of the vessel. Some lipids remained sedimented at the bottom, while some had cream to the top. However, by the end of digestion, all the lipids had cream to the top of the digestion vessel. In hot milk, however, the lipids, which are indicated here in orange color, in the middle of digestion were all sedimented to the bottom of the vessel, and by the end of digestion they remained sedimented to the bottom of the vessel, and none of them creamed to the top, as what happened in the cold milk. So if we were doing this in vivo, we might see that nutrients are emptied at different rates when we drink cold milk compared to hot milk. During the digestion of cold milk, lipids will tend to float to the top of the stomach, and this may delay the gastric emptying of nutrients into the small intestine. However, in hot milk, the lipids seem to be entrapped within the protein matrix and sediment close to the pylorus. Therefore, we can conclude that drinking hot milk may increase the rate of gastric emptying of nutrients to the small intestine. So why does this happen? So this led us on to our next study on enzyme activity. So pepsin is the major enzyme related to protein digestion in the gastric phase. Pepsin activity is determined by both pH and temperature. So based on this, we created a pepsin activity prediction model. We did this for human pepsin, where we can see that in the areas in red are areas of high activity, which are around 37 degrees and pH 2. And we also did it for porcine pepsin. By looking at these graphs, you can clearly see that the human pepsin has a broader range of pepsin activity based on temperature and pH compared to the porcine pepsin, which has a more narrow area of high activity. So based on hemoglobin as our substrate, we can see that in cold milk, when we drink cold milk, as the temperature of the stomach, or the temperature of the milk, will increase to 22 degrees by the time it gets to the stomach, and the pH will be at around 6. Using our model, we calculate that our pepsin activity will be at approximately 0.36% of the optimum activity. However, when we look at hot milk, the temperature by the time it gets to the stomach will be 44 degrees. The pH will be again at around 6, but we have an increased pepsin activity to approximately 4.6% of the optimum. This may be what led to the difference in the movement of lipids during the digestion of hot and cold milk in our previous study. Now, it must be said that this is based on hemoglobin as a substrate, but when we look at other studies that look at the activity of pepsin, we can see that pepsin activity is higher at higher pHs on other substrates, for instance, casein. So we made these models, and the idea was that anybody that's doing in vitro digestions would be able to use this pepsin activity prediction model. So currently there is a pepsin activity model hosted on our Shiny applications. In this model, you can input your data for either human or porcine pepsin. So you enter the time, the temperature, and the pH all in one go, and you can enter all your data in one go. You click add data, and you get a result such as this. So to explain this, here we have the predicted pepsin activity of porcine pepsin throughout a gastric digestion over 10 minutes. So we can see that we predict, based on our temperature and our pH, that at the start of digestion, the activity is going to be quite low, and then as we increase temperature towards 37 and pH decreases towards pH 2, that we increase our porcine pepsin activity. We can then compare this to human pepsin by inputting the same data, and here we can see, because of the broader range of human pepsin, we reach the optimum activity of pepsin quicker in human pepsin compared to porcine pepsin. So any user of in vitro digestion will be able to input their digestion data into this model. They will be able to get a prediction of the porcine pepsin activity that they're using in their in vitro digestion, and then they'll also be able to compare this to human pepsin. The good thing about this model is that this gives you a percentage of your optimum activity. So if you have a porcine pepsin that has an activity of 2,000 units, you can also compare that digestion to a digestion that used a porcine pepsin that had an activity of 1,000 units. So we're near the end. There's another overview of the thesis. Chapter 1 was our literature review. We also looked at the intrinsic factors, which was the impact of beta-lactoglobulin on yogurt digestion, the impact of low versus high pasture allowance on lipid digestion, the extrinsic factors such as the consumption temperature of milk, and finally the influence of pH and temperature on human versus porcine pepsin activity. There were several outcomes from this thesis, such as published papers, co-author papers, and grants received. And then I finally just want to say thank you to all of my supervisors, Andre, Tom O'Callaghan, Seamus Mahoney, and a special thank you to Daniela Freitas. And I also want to thank the amazing food chemistry team in Moorepark for their friendship and guidance throughout my PhD. We made a lot of very good memories, and it is a time that I very much enjoyed. So thank you all for listening, and I'm open for any questions.
Thank you, Conor, for your very nice presentation. So now I have a few questions. So the first one is, why did you choose to study beta-lactoglobulin?
Thanks, Cynthia. So I suppose beta-lactoglobulin, I suppose, is the primary whey protein in bovine milk. There's it has heat-induced denaturation during milk processing, and that facilitates kind of the interaction with kappa casein that allows the gelation and then the viscosity that you see in yogurt. I suppose we chose yogurt as a dairy product rather than just raw milk due to beta-lactoglobulin's resistance to gastric digestion in its native form. But when we denature beta-lactoglobulin, we kind of increase its susceptibility to gastric digestion. But then I suppose in my literature review that I mentioned, I found differences there in gelation properties of beta-lactoglobulin A versus B when beta-lactoglobulin was isolated, but I wanted to study it really within skim milk as a system. I suppose then we wanted to look at beta-lactoglobulin A versus B due to that difference in gelation properties, and also I suppose on a more national level in Ireland, I suppose Ireland's national dairy herd is moving towards a precision dairying system and the use of genetic selection to improve certain milk production traits. And I suppose while we're doing that, it can be good for certain areas, but we also want to make sure that if we're optimizing one trait, such as the milk yield from cows, that we don't negatively impact other areas of the dairy processing chain, such as yogurt production.
Okay. Thank you. The next one, I think, is more related with your prediction model. Can you give a further explanation on how to use the pepsin activity prediction model?
Yeah, I can. So I suppose when we were designing the pepsin prediction model, we wanted to ensure that as many people as possible could use it. So that's why we based it on the INFOGEST, so the INFOGEST standardized protocol, where they suggest using the pepsin activity model with a pepsin activity experiment with hemoglobin as a substrate. So if a researcher wants to use this model, they can go and study the activity or find the activity of their pepsin using the protocol outlined in the INFOGEST digestion paper. And then once they have that, they can go ahead and use and do their digestion. During the digestion, they should make sure they collect the data on the pH and temperature as the digestion happens. And then once they have all that data, they can input it into the model. So then the model will be available. Currently, it's available on an R Shiny app, which is hosted online. and the link I believe is being sent out or is on the bottom of the YouTube video. But we're also have this paper. It's in the process of being published. So if it gets accepted for publication, there will also be an Excel sheet with the publication, and researchers can use that Excel sheet to predict the pepsin activity.
Thank you.
I think we have another question in the Q&A section. So this question is from George Van Aken. Do you think that let's say the composition of the peptides will be different, for example, in relation to bioactive peptides?
Yeah, it's a good question. I would imagine that there definitely could be some differences. So, for example, if you look at the two models, you can see that the porcine pepsin model or the human pepsin model has a broader range of digestion, and that could lead to a more extensive hydrolysis of the peptides. So yeah, I'm sure that there could be some differences in the release of bioactive peptides, but we didn't look directly at the differences in maybe hydrolysis sites. If that could be an interesting thing to look at, we try to investigate if there's different hydrolysis sites within the protein between the porcine pepsin and the human pepsin.
And I have another one. Will using a different substrate for the pepsin activity model impact the result?
Yeah, so that's actually a question that we would have been interested in studying, I suppose, if I had more time on the during the PhD. So definitely, I would say that using a different substrate would impact the results. So as I said in the present study, like we use the hemoglobin as a substrate because of its use in the standardized INFOGEST protocol. And that allows really, as I said, that anyone can replicate the assay using that standardized protocol. But I suppose there's been several other studies like Cells et al. Was the one that would pop to mind straight away, where they looked at pepsin activity on different substrates like casein and egg white, and they found quite different pepsin activity on those substrates compared to something like hemoglobin. And I suppose a further study or something that I think should be done in the future would be to look at these substrates and create pepsin activity models for these substrates, and even go as far as doing it for novel proteins like plant proteins, so that you could really further understand the digestion, the pepsin activity that's happening in your specific digestion.
Thank you. And I have, I think, the last one.
Yeah.
How did you decide on the temperature curves used in the consumption temperature studies, and how did you implement them?
Yeah. Okay. So I suppose we really decided that goes back to the literature review. We decided on the temperature curve based on, it was mainly on 2 in vivo studies that was carried out in humans. I suppose one had the participants consume orange juice at different temperatures, and the other had participants consumed coffee at different temperatures. And I suppose they didn't consume milk as we did in our study, but we assumed that the temperature curves would be similar. So we really wanted to simulate the results from the in vivo findings as closely as possible. So we used that kind of a temperature ramp using a water bath and a cryobath. So I suppose we could have started the gastric digestions at either 4 degrees or 60 degrees or 37 degrees, the starting temperature of the milk. But I think that would have exaggerated the results maybe more than what actually would be seen in vivo. So that's why we wanted to stick to those the simulated temperature curves that we saw in the in vivo studies.
Thank you. And I think that one was the last question. So thank you, Conor.
Thanks
Yep.
very much.
Thanks, Conor. Really nice discussion and your presentation as well. So now I'm gonna share my screen so I can present the next webinars. So for our next webinar in April, we will have Doreen Jens from KU Leuven from Belgium. And then in our webinar for May, we will have Sara Perez-Vila from Teagasc in Ireland. And then we are still trying to find speakers. So if you are interested on presenting your research of your PhD, just keep such out. So we have available position for June, July, and August, and just send us a express of interest, and then we will see this. So that's it. So thank you so much for everything, for all the attendees, and then thank you again, Conor, for your presentation and the discussion. So see you